2, and in this part we're going to discuss about sample complexity and the finite hypotheses, which was the main goal, and consistent case. So what does consistent case mean? So let h be a finite set of functions from x to 0 1, and L be the algorithm, whatever concept C which belongs to the class h, and sample and the overall the idea is that the algorithm returns a consistent hypothesis, which means that the empirical risk is 0. Consistent means that on all the samples that you gave the algorithm during training, it's right on everything. So it's a consistent case, which is not really how it happens in practice, but let's study it for now. Then for any delta greater than 0 for finite hypotheses, whatever hypothesis that has returned, the algorithm has returned, the risk will be less than 1 over m log number of hypotheses log 1 over delta with probability at least 1 minus delta. Again, so now the pack learning, you can forget the pack learning discussion altogether. We're going to start looking at bounds now, which will be of this form, that the risk is less than something something for high probability, with high probability. In the end, this again translates to the kind of bounds that pack learning was talking about, but we are not really concerned about how many samples do you need or etc., like polynomial stuff or whatever. This is really a high probability generalization bound. That's the entire discussion now. So let's say for any, you fix an epsilon and you define the subset of the entire hypothesis class. Capital H is the hypothesis class, and H sub epsilon is all the hypotheses where the real risk is greater than epsilon. So what we will try to do is see if this is the hypothesis class where the real risk was greater than epsilon, right? And now our algorithm has returned a hypothesis for which the empirical risk is 0. So we're going to compare, like, what is the probability, like how can we end up with an algorithm with a hypothesis for which the empirical risk is 0, but the real risk must be greater than epsilon. Only then are we violating those conditions, right? That the real risk is greater than epsilon with probability something something. And if you're able to get a handle on this, then we can comment on the real risk being less than epsilon by just reversing the probability or whatever. So we want to prove that with high probability, h sub s is consistent, then it has low error. That means if h sub s has empirical error 0, then it must not be in this set h sub epsilon for which the real risk is greater than epsilon. So the probability that the empirical risk is 0 implies that the risk of h of s is less than epsilon. That's what we need to bound. That the probability that this is 0, what is the probability that if the empirical risk is 0, that implies that the real risk is less than epsilon. And we want to bound that with minus delta. Equivalently, we can say that the probability that this empirical risk is 0 and the risk is greater than epsilon, the real risk is greater than epsilon, is less than delta. All we did was just flip this sign, and then this becomes less than and this becomes 1 minus delta. Basically 1 minus delta of this entire statement. Or what we can say is that the probability that the risk is empirical risk is 0, but this belongs in this bad set. Let h sub epsilon be a bad subset of the hypothesis. So the probability that this risk is 0 and it belongs to this bad set, and if that probability is less than delta, then we would have figured out, then we have of such a form that with probability 1 minus delta, it has a real risk of less than epsilon. Anyway, so now for all h's in the entire hypothesis, class, for every hypothesis, and because it's a finite, we can write it, like we can enumerate it or something, right? Its empirical risk is 0 and it belongs to this bad set. Or we can say that for a hypothesis in the bad set, the empirical risk is 0. This can be done in these many ways, that the first hypothesis has an empirical risk 0, or the second hypothesis has the empirical risk 0, or the third hypothesis has the empirical risk 0 in this bad set. What we're trying to say is, what is the probability that we picked something in the bad set and it had an empirical risk of 0? How can that be that we picked the first one and its empirical risk was 0? We picked the second one and its empirical risk was 0, blah, 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 up to the number of elements in that bad set. And by the union bound, it will be less than just the number of just the sum over all hypotheses, and the probability sum of all hypotheses in the bad set here, and the probability that the empirical risk is 0, right? This is always be less than because of the union bound. So now when can the empirical risk of this algorithm be equal to 0? Well, if it's a bad algorithm, that means its real risk is greater than epsilon. And if its empirical risk is 0, that means it did not make any error on any of the m points. So if its real risk is greater than epsilon, that means probability that it makes an error is greater than epsilon. Probability that it does not make an error is less than 1 minus epsilon. For all m points, it's like saying 1 minus epsilon to the m. For all of these hypotheses in the bad set. So that's like a union bound, way overkill, but that's how we do this. And that then is less than the totality of this, because the number of elements in the bad set is less than the overall number of elements. Again, an overkill. That's how we do it. And again, 1 minus x less than epsilon to the e to the minus x, and we get that bound. It's a pretty simple thing. The main key idea was to say that if it has an empirical risk 0, what is the probability that it had an actual risk greater than epsilon? And if it had an empirical risk 0, that means at every point it was correct, and that can only happen with probability less than 1 minus epsilon, because the probability of it making an error is greater than epsilon. And therefore we get to this number, that the probability that this thing is bad is less than blah, and then we can set this as delta, and we can get to here. Like, this is just, now that's a bit that you have to do. And you can see if I set this as delta, what happens is I take the log, because I want to get I want to be able to comment about the, like, I want to write what epsilon is. So I set this equal to delta, and then epsilon is log h plus log 1 over delta divided by m, and that's it. Because I set this as equal to delta, I take the epsilon, I take the e to the minus me on the other side, and I bring the delta down. So this becomes mod h, cardinality of h divided by delta, and I take the log, which becomes log of the cardinality of h plus log of 1 over delta, and then I divide by the m from the right hand side, so it becomes this particular quantity. It's something that you write, and it's pretty easy if you see. So the probability that I selected from the bad set is less than this. So that means the probability that it's from a good set is greater than 1 minus delta. And I set that as delta, so the risk will be this less than. Yeah, because I'm trying to calculate what the epsilon is, and the risk is, this entire thing is when the risk is great, like the probability that the risk is greater than epsilon, because we were in setting. So this entire thing says that the probability that an hypothesis is selected for which the empirical risk is 0, but has the real risk greater than epsilon, the probability that happens is less than this. And you can write it, probability blah greater than epsilon is less than something. So probability that blah is less than epsilon has to be greater than 1 minus delta, and this would be delta. Again, fine. So the algorithm can be an empirical risk minimizer if problem is realizable. Error bound is linear in 1 over m and only logarithmic 1 over delta. And log h2 is the number of bits used for the representation of h. Bound is loose for a large number of hypothesis sets, right? And it's really uninformative for infinite hypotheses. Like, how would you do that? An example then is a conjunction of Boolean literals. Let's say you have, for n equal to 6, let's say you have 6 particular variables, and what you need to do is, what you are given is, what are the values basically. Okay, what you actually have is this formula, this particular thing, that there is some conjunction of Boolean literals which you do not know. A conjunction means and operation, right? So it could be x1 or x1 bar, or x2 or x2 bar, or x3 or x3 bar, and blah blah blah, and it has to be a conjunction of them. You don't really know what the real conjunction is, but you are given a particular kind of truth table, that if I assign values 0 1 1 0 1 1, then I have the positive output, or if I assign the value blah blah blah, then I have the positive output, etc etc. So the algorithm is that you start with the entirety of the thing and rule out literals incompatible with positive examples. Fine, that's fine, whatever. What you really output then is any 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 conjunction which is consistent with the input that you're given, because the number of possible conjunctions that you can actually have is 3 to the n. Here I want to tell you why. The number of possible hypotheses you can have is a finite number, 3 to the n. Why? Because either x1 is present with a plus, with no negative, or x1 is present with a negative, or x1 is not present at all. So every literal has 3 choices. So that for total for n choices, you have 3 to the n number of hypotheses, and you return any one which is like consistent with it. So the problem is learning class Cn of conjunctions of Boolean literal with at most n variables. So algorithm is to choose h which is consistent with s, and there is some algorithm somehow, I don't care. Since the number of hypotheses are 3 to the n, sample complexity then is m has to be greater than 1 over epsilon. Coming from here, if I want this thing to be less than epsilon, then I need to be that m has to be greater than 1 over epsilon log of hypotheses plus log of 1 over delta. So m has to be greater than 1 over epsilon log 3 to the n log over, and this thing is whatever, like you need these many samples. So computational complexity is polynomial. Since algorithmic cost per training samples is fine, whatever. That's basically, this is an example for consistent case that you need to be able to comment on the cardinality of h, at least for finite hypotheses. Now we'll look at finite hypotheses and inconsistent case.